All right, lesson 9.7, Taylor polynomials and approximations. Okay, so what is a Taylor polynomial and why do we need it? So it's a way to have a polynomial function approximate some non-algebraic function. Okay, we'll see it with sine, cosine, inverse functions, logarithmic. And then just to check this picture out. So here's f. Here's some non-algebraic function. We're saying, all right, let's create a polynomial function where we can use the behavior of that polynomial function to approximate the behavior of another function. Okay, we've done this before. You've done this before in Newton's method where we approximate the values of a function using another function. So a couple things have to be true. Okay, notice that the polynomial and the function, they have to share the same y value. Okay, so we can think of it, if this is a line of tangency, well then the first derivative of the polynomial and the first derivative of the function are going to be the same as well. All right, now as we see, increasing the degree of the polynomial will make the approximation that much better. Okay, so if you only look at the first derivative, well then that's going to be a limited approximation. The closer that you get the polynomial to the function, the better the approximation will be. All right, so copy these down, have these in your notes to reference. Definitions of your Taylor and Maclaurin polynomials. Okay, so if a function has n derivatives at a center, all right, they're centered around some value, and that would be this, okay, wherever that point is that we're using the polynomial to approximate the function. Then the polynomial, this nth degree polynomial, this is the nth Taylor polynomial for f at some point c. If c is equal to 0, so if it's centered around 0, then the Taylor polynomial is just known as your Maclaurin polynomial. So the Maclaurin is actually a little bit easier, and you'll see when we do an example. But what you need to understand is this right here. This is your bread and butter. This is your coefficient to every term in your Taylor or Maclaurin polynomial. So look at this. This is the nth derivative at c. Okay, in a Taylor polynomial, c will be a number that's not 0. In a Maclaurin, c will always be 0, divided by n factorial. Okay, so that's going to be your coefficient. That's what we're going to continue to work with. All right, so finding the polynomials are very easy. Okay, n is the degree. That tells us how many derivatives we need. So we're going to find the Maclaurin polynomial for sine function, 5th degree, okay? And then remember, this is and we're evaluating it at 0 all over n factorial. That's going to be our coefficient. Okay, so first things first, we need the value of the function at 0. So sine of 0 is 0. And now, because it's a 5th degree, we have to go up to our 5th derivative of the function. Derivative of sine is cosine. Second derivative, negative sine of x. Third derivative, negative cosine of x. Fourth derivative, positive sine of x. And then our 5th derivative is positive cosine of x. Okay, so once you find your 5 derivatives, now we evaluate the derivative at that center, so at 0, 1, 0, then we get negative 1 in the third derivative, the 4th derivative will be 0 again, and the 5th derivative will be back to positive 1. Now the sine, cosine, e to the x, and 1 over 1 minus x. We will study those in depth in each section. So you're going to see something that happens here. All right, these aren't just my coefficient though. My coefficient comes from the value of the derivative at 0 over n factorial. So now when we put it back together, okay, the 5th degree polynomial approximation, f of 0 is 0. So look at where I start. I start at my coefficient of x. So this would be 1 times x. Now my next value, the derivative, would be the third derivative. So minus 1x cubed. And then I have to make sure that I divide by n factorial. The coefficient to x to the fourth is 0. And then the coefficient to my x to the fifth would be positive 1 again. So plus 1 times x to the fifth, all divided by 5 factorial. Now cleaning this up a little bit, fifth degree, x minus x cubed over 6 plus x to the fifth, and then 5 factorial is 120. Now, do you have to go to this part? You need to know that these are equivalent. Okay, I don't mind if you keep it in factorial notation, but if you're checking your answers, then at least know that those two answers would be equivalent. Now check out here the fifth degree. That means your highest power is x to the fifth. It's not necessarily 5 terms, and we'll talk about that difference again in later lessons. So it's just a matter of finding a derivative, dividing it by n factorial, and then making sure that we actually have the polynomial, and that's represented by x to the n. All right, so f of x is 1 over x plus 1, another fifth degree. So let's start with f of 0. F of 0 is 1. Okay, Maclaurin polynomial automatically, that tells us that we're centered at 0. So if I write f of x as x plus 1 to the negative 1, so we're finding up to the fifth derivative here. Negative 1, x plus 1, negative 2. Second derivative, positive 2, x plus 1 to the negative 3. Third derivative, negative 6, x plus 1 to the negative 4. Fourth derivative, 24, x plus 1 to the negative 5th. And then my fifth derivative, negative 120, x plus 1 to the negative 6. Now, you don't really need to concern yourself with rewriting these derivatives nicely because we just care about the value of the derivative. So f prime of 0, negative 1. Our denominator is either going to be, your denominator is always going to be 1. So you just have to make sure that you're keeping the coefficient positive or negative. Second derivative, positive 2. Oop. Third derivative, negative 6. Okay. Fourth derivative, positive 24. That should be at 0. And then the fifth derivative at 0, negative 120. Okay. So now don't forget, this is where our coefficient, we have to then divide these values by n factorial. So our answer would look like fifth degree polynomial x. All right, so we have to start at f of 0. The sine function did not have that. So f of 0 minus 1x plus 2x squared divided by 2 factorial minus 6x cubed divided by 3 factorial plus 24x to the fourth over 4 factorial minus 120 x to the fifth over 5 factorial. Now, the importance of being able to simplify these is now you should see all of my coefficients cancel. Plus x to the fourth minus x to the fifth. Okay, and we'll chat about this in class. But this would be the fifth degree Maclaurin polynomial to approximate the function 1 over x plus 1. Okay, so now the nth Taylor polynomial centered at c. So notice now it's centered at a different value. The steps remain the same, but now we're evaluating the nth derivative at c, where c is not equal to 0. But the coefficient still comes from the value of the derivative divided by n factorial. Okay, so first things first, we'll start at f of 4 because that'll be our first term. Square root of 4 is 2. All right, now we only need a third degree, so I just need to go to the third derivative. So first derivative, 1/2 x to the negative 1/2. Repeating the power rule, second derivative, negative 1/4 x to the negative 3/2. Third derivative, that would give us positive 3/8 x to the negative 5/2. Okay, so next we evaluate the derivative at each of these values of c. First derivative at 4 would give me positive 1/4. Second derivative at 4, that would give me negative 1/4. Square root of 4 is 2. 2 cubed is 8. And then the third derivative at 4, just give me 3/8 times, again, square root of 4 is 2. 2 to the 5th power is 32. All right, so now putting these things together, third degree polynomial. First term is f of c, so that would be 2 plus 1/4 times, now when it's centered at c, the polynomial would be x minus 4 to the first power, and then minus 1/32, x minus 4, quantity squared, all over 2 factorial, and then plus 3 over, so that's 240 and 16, 3 over 256, times x minus 4 to the third power, all divided by 3 factorial. All right, so let's clean this up a little bit. So my third degree Taylor polynomial, 2 plus x minus 4 divided by 4 minus x minus 4 squared all over 64. And then plus, when 3 factorial I know is 3 times 2 times 1. So I can cancel that 3. And I get x minus 4 quantity cubed all over 512. So that would be my final answer. All right, let's see what the next one is. Okay, so complete this for me. All right, fourth degree Taylor polynomial. So you'll need to find for me up to your fourth derivative. And then evaluate your derivatives at 2 and get for me the fourth degree polynomial approximation.